Hey, I have a project due tomorrow about some random mathematician named Emmy Noether. I've looked everywhere and still can't understand anything she has done. Do you have any suggestions to help me?
I know just the thing. Go down to the basement.
What does this thing look like again?
It's like this really old black box that has a cord on it.
Oh, I found it.
Okay, now to use it, you dial 101 and then the year you want to research.
Okay, perfect. Thank you.
You gave me a fright. What are you doing here? And why are your knees showing?
I fell on my way here. Listen, it doesn't matter. My name is Paige, and I was wondering if I could ask you a few questions.
I guess.
First of all, how's your theorem coming along?
You mean my thesis? The one on algebraic invariance? I mean, it's hard work, but it's finally nice to have a chance to get a PhD, so young women can go to school a few years ago. So I can't really complain.
Uh-oh, I think I'm too early. I'll see you later. Remember me?
Weren't you the one who randomly showed up during my PhD research, then magically disappeared?
Yep, that's me. Listen, I need a favor. I need to know about your current theorem.
Well, I'm just finishing the publication now. Come look. For every conservation law, there's a continuous symmetry in a physical system that is associated with that law. So everything in this bracket is constant for that equation. So when energy is conserved, that's because of translation symmetry in time, whereas momentum is conserved due to a translation symmetry in space. These physical symmetries result in a conservation law, which is our constant. A simple example of this is if two pool balls were to collide, they would collide in the exact same way regardless of where they are on the pool table.
Oh, I got it. So if there's a conservation law, there has to be a symmetry. This finally makes sense. Now what about your second theorem?
This one isn't too refined yet, but it's basically my first theorem, except it applies to specific infinite dimensional symmetries. So for example, rotational symmetry, it explains the conservation of angular momentum.
Wow, this finally makes sense. Hey, I'll see you in a few years.
Oh, where is she?
I was wondering when I'd ever see you again.
What are you doing now? I thought you already published both your theorems already.
I have. Now I teach my boys non-commutative algebra.
That's cool. Tell me more.
So right now we're looking at ring theory, specifically non-commutative rings. So that's when the multiplication is not commutative. So A and B exist as long as AB and BA don't equal each other. They're not the same. And
I'm going to stop you right there because I think this is past my high school level of knowledge, so.
I was afraid you were going to say that. I feel my boys are the same way. I don't think I'm really leaving an impact on them. I don't think it's worth it anymore. Like, I don't even get credit in this field anyways.
Let me stop you right there because that's not true. Let me show you something. Here, look.
Emmy Noether's mathematical contributions not only changed the world of physics, but her work is also the foundation of abstract algebra. She inspires women in mathematics and science as her work and hardships are still relevant today.
Look, this is how important this class knows how important your theorems are to math and physics.